The topic of this video is continuity. We will discuss continuity on open interval, continuity on closed interval, and then based on graph, we will identify one-sided limit. In my previous video, I already discussed or solved the problem of with one-sided limit algebraically. Now we will do by graphing. So, continuity. What is continuity in the term of math? It's when the function f is continuous on at the point some interested us point, and it doesn't have any interruption on the interval, be it open interval, be it closed interval. When I'm saying open or closed interval, what do I mean by that? Remember, we know that when we mark down on the line of numbers, okay, open interval is when we mark down with parentheses, which means these final points A and B are not included. And closed interval when we mark down our interval with square brackets, which means this point A and B are included. So to show open interval on the graph, it can be like this, and points are not included. But to show the same graph on closed interval, it's gonna be like this, because these points are solid. Circles are solid, that means the circles are included. When circles are empty, that means they are not included. So this is for understanding open and closed interval. Okay, so here we are going to explore continuity on the open interval. As you can see, here you have on A, we have open interval A and B. Why? Because I have empty circles, yes? Here is also open interval A and B. Here also open interval A and B. So right now we are going to explore continuity on open interval. So what can we say? Looking at the graph A, we'll see that we have at the point of C, we have here a whole circle at where we cannot define the function f of c, right? Function f of c at the point of C is not defined. Why? Because we have empty circle. Okay. When we look at the graph B, what we can say? It's why do we say it's not defined? Because we have continuity from both sides, right? Look here. Continuity from both sides, from the left side, from the right side. It's just at the point of C, the function is not defined because it's a hole. It's a circle, empty circle. Now on the graph B, on the other side, we have here break, right? Therefore, the limit of function doesn't exist here. The limit of f of x, where x approaches to C, it's right here, doesn't exist. Now, you can ask me why on the graph A we said not defined, and on B we said limit, we take limit. Here value, there we take a limit. Because At the point of C, there is a break there, so therefore we have to explore what is in surrounding. But on the graph of A, there is no interruption on the graph besides in the point of C. Therefore, here we are saying that at the point of C, the function is not defined, and anywhere else is defined, interrupted. It's uninterrupted, the graph. But when we are talking at the point of C on the graph B, then we have interruption. So there is a gap between these two graphs. Therefore, when there is a gap, we are talking about limit. We can only approach. But when the graph is continuous and only one point, we are talking about definition of defining function at that point. This is why in one case we take just the point, in another case we take limit. Okay, in the case of C, what we can say that at the point of C, we can say that f of C, okay, let me write down here. Actually, I can delete this, we already explained. So f of C, we can say that f of C is not equal to limit f of x, because it's both of them are in the point of C when x approaching to C. Why? Because f of C here is defined. Let's say is equal some d, right? But here on the graph, it's right here. Ooh. Let me take smaller. It's right here on the graph. It's not defined, right? Look at the A, similar. F of C. I don't want to put f of C again, so there won't be confusion. That's why I will put limit f of x. X approaches to C is not defined. Or I can put 0.1 and here put 0.2. That would be the best. And I will put this way. F of C, number 2, 0.2. F of C, 0.1. 0.1, 0.2. Is not defined. Okay? That's why they are not equal. Okay. So, what we can say about all this? About continuity at a point. Yeah, let's generalize. The function f considered continued at the point of C when so red color, continuity, at the point C, at the point, okay, point C. So when f of C is defined, second condition, limit f of x where x approaches to C does exist. See, that's related to graph B, so limit doesn't exist. And third condition, when limit f of x, where x approaches to c, is equal to function f of c. So, getting familiar with the discontinuity, to continue the topic, there are two types of, two categories of discontinuities. While some discontinuous can be removed, some of them cannot be removed. Let's say, just like in life, math is the model of life cases. Let's say you are facing a big hole in front of house, so some hole that is not big enough, right? And if you fill it up, you can walk by, right, and continue walking. Then that will be removable hole, removable discontinuity. But if you have hole that even that you cannot remove because it's too big, okay, or there is further some other obstacles, so there is nowhere to go, let's say too many stones or mountains, there is not much place to go, then such such discontinuity is non-removable. Now, how can we identify on the graph and algebraically, I can show you also, which discontinuity is removable and which discontinuity is not removable? So I'm going to use 3 examples. One is going to be f of x is equal 1 over x. If I draw the graph, it's gonna look like, shape is gonna be like that. Okay, so what can we say based on graph discontinuity at the point of 0? Is it removable? No, obviously it's not. There is it's not continuous in the surroundings of 0. So if we would excuse me, if we would remove that the whole, it would make it continuous. And looking at algebra, algebraically, the 1 over x cannot be equal 0. And that's why it's non-removable discontinuity. Let's take another example. G of x is equal x squared minus 1, x minus 1. The graph of this rational function is some of you might be surprised how graph will look like. Okay. Is it equal? Yes. Okay. So let's see what it is, why it looks like that, and if it's removable or non-removable. So looking at the domain of the function, at the bottom we have, in denominator, we have x minus 1, which means x cannot be equal 1, yes? Now let's do simplification. X squared minus 1 over x minus 1 is equal. X squared minus 1, it's like a squared minus b squared. I can open it x minus 1, x plus 1. And here x minus 1, canceling. And I have only x plus 1 left. And this is where from x plus 1 and the linear function, and this is where from I mark down the 1. Because when x is equal 0, y is equal 1. Okay? Now, where from this 0 at the point of x is equal 1? This is this one. Cannot be equal, x is equal 1. If it cannot be equal, that means we have their whole. So at the point of 1 and 2, we have whole. How did that figure out that it's 2? Because if x I plug here 1, 1 plus 1 is 2, right? So at the point 1 and 2, we have we have whole. But is this whole removable? Absolutely, because in surroundings of that the whole, we have continuity, right? And here it is, but in the algebra, this treatment of the whole, it shows that we can get rid of this dangerous denominator. It can turn into 0 and get just x plus 1, where x can be anything. That's why if we treat, it's going to become like this. It's treated. Okay? But right now I'm leaving, so you can look at the graph, and what that means, it is removable discontinuity. Removable discontinuity. Okay? And the other one, let's see. I'm going to use h of x is equal x plus 1, where x condition less equal 0, and x squared plus 1 when x is greater than 0. All right, so if we draw this graph, we are getting x plus 1 where x is less than 0. So if this is my 1, so my graph is going to go only to when x is negative, and including this one also, 1 also. This is negative 1. Like that. That's it. Okay, this part only, we take one part because we are limited by condition x is less than 0. So x is greater than 0. We don't take it because there is no, it's limitation of condition. And the other part now, where x is greater than 0, we are going to use x squared plus 1. So we have here already plus 1. So x squared is going to go from here like this, only this part. Yes? And that will be, so this one, let's see, I can do this way. Okay, well, I can do this one. That's funny. Ah. Here we go. Weird, it's not taking. That's okay. Um, I can go this with this color. Okay, and let me try this piece also. Maybe this one will work. Yeah. And this is our graph. Now, what do we have? Do we have on this graph, algebraically or on the graph, do we have any limitation? No, we don't. So we have on domain. So that means it is continuous on entire real number line. Yes? And there is no the question of removable or non-removable discontinuity. This one is absolutely continuous on entire line. Even if I would take, let's say, another continuous function, if I would take y is equal sine x, it also would be continuous graph, right? It's absolutely continuous on entire real number lines, continuous. Okay, let me fix also. Continuous. Okay. So now let me explain also continuity on a closed interval, and then we move to examples. So we have closed interval because this we don't have hole, it's a solid circle, which means it's included on the graph. Therefore, we are going to this interval marked down as a square bracket, a and b. So the function considered continuous on closed interval where there is no any type of interruptions, hole, jumps, and breaks, and so forth. So, which means it's not. We see it continues. Now, how to define mathematically that? So the function f is continuous on the closed interval a through b. When f is continuous on the open interval, if it's continuous on open interval AB, and okay, let me make it mark it down as a the condition. So continuous on the interval closed interval A and B if continuous on interval open interval AB, and condition number 2, when limit f of x where x approaches to a from the positive side this way, okay, a from positive side equal f of a, and indeed it's going to be equal f of a this point, and limit f of x, where x approaches to b from the negative side, from here, so we're just encapsulating in the interval, b from negative side, is equal f of b. And f of b is this point, right? Because it's solid. All right? The function f is continuous from right at a and continuous from left at b. So between these intervals, and that's what continuity on the closed interval. Let's use a couple of examples on continuity on the closed intervals. Make space. So here is example on continuity on a closed interval. F of x is equal square root 1 minus x squared. Here, half of circle, here we have. So we have radius 1, because x squared will be equal 1, and so on. So the radius is going to be 1 here. So let's find, and it's going to be identified at closed interval from negative 1 to positive 1. Okay, let's see if it's continuous. So we have to take at the point 1 approaches from the right, negative 1 from the positive 1, and it's going to approach to this one from the left, and it's going to be from the negative side approaching. So we are taking limit square root 1 minus x squared, and x approaches to negative 1 from positive side, and then we are going to take limit 1 minus x squared, x approaches to 1 from negative side. So what do we get when x approaches to negative 1 based on graph? When approaches to negative 1 from the positive side, it approaches to 0, right? F of x at this point is equal 0. And let's see, we have also solid point, so how much is f from f of negative 1? X is negative 1, it still equals 0. Yes? So from the right, it looks continuous. From this point, it's continuous. Now, approaches from the left, it's going to be equal 1, right? At positive 1, where f limit is going to be 0, right? Okay, and at the same time, f of 1, it's going to be equal, again, 0. Yes? So, and it is still continuous. If both limits, one side limits, are continuous and they are equal to each other, then we say the function is continuous. Function is continuous. On interval negative 1, positive 1. Okay, and let me take one more example on this case. So this one is interesting case. So let's assume we have such function. And then from here, All right. And our closed interval, we are taking A and B. So let's say if I take, well, this is point D, or let's take C, and let's assume this is 2, this is 4. So let's take it. Limit f of x, where c, x approaches to c, from the negative side, okay, and limit f of x, x approaches to c from the positive side. All right, as we approaches from the negative side here, it's going to be equal 4. Why? The whole graph is on the left side, right? And when it's approaching from the positive side, this way, it's going to be equal 2. Because since both n hole and solid point have on the same line of C, if you wonder why in one case I am taking hole and the other case I am taking 2 and not vice versa, like I said, the graph of the hole ends with hole. It's on the left side where for the negative approach, from negative side approach. And the graph, when it's approaching from the positive side, the graph located on the positive side first. Okay, therefore it's going to be taking the solid point. All right, so it's equal to, so because at the limit f of x, where x approaches to c, does not equal limit f of x, where x approaches to c plus. Therefore, it's not continuous. Also, because the limit f of x at the point of c does not exist. Because the y doesn't exist, because let's say here is point. We have here point. If I take the point here, there is no value, there is no graph there, right? Okay. All right, said that, now let's move on with more practicing case. Well, let's assume we don't have all this. I'll go over. Yeah, the rest I cleaned it. I forgot to clean this one. So we have the graph, and as you see, we have the full point. So this is like a treated whole. Remember the case when we had x squared minus 1 over x plus 1, x minus 1. In this case, it will be, because we have increasing graph left. So when we factor it down, x minus 1, x plus 1, x minus 1, this is gone, we have x plus 1 left. And x cannot be equal 1. Since we have only x plus 1 left, then there is no whole left. So which means we removed the whole and we have left only the trace of that whole. That's what it is. Okay? That's where from we can pop up such a point there. All right, so this is at point 7. So when x approaches to 7 from the positive side, it's going to be equal 6, right? When it's x approaching to 7 from negative side, it's going to be still equal 6. Yes? So since limits are equal, and how about at the point of f of 7? It does exist, right? It's equal 6. So when limit is equal, the same, then, because limit f of x is equal, limit f of x, in this case x approaches to 7 from negative side, x approaches to 7 from positive side, and it's equal 6. Therefore, it is continuous. Plus, if I take f at the point of 7, it's going to be equal 6 also, right? All right. Now let's do this question, number 2. I'll move a little bit away. There we go. So this is our point 4.5. Let me fix it. Wasn't precisely 4.5. Well, okay, it's falling exactly on 4. Then I'll take this. Even better. Working with a whole number is much more pleasant than from 4 from negative side to 4 from positive side. So what we have, we are approaching to 4 from negative side. It's approaching to what? 5, right? It's equal 5. From the left side, from the right side, from the positive side, it's to 4, it's going to be equal again 5. All right. Now, since left side equal at the limit is equal to right sided limit, we should insist that the limit does exist at the point of 4, right? I should insist that limit f of x at x approaching to 4 does exist. Okay? But because we have here this point f of 4, let me use this color, f of 4, if I take f of 4, how much is equal? It's equal 7, right? So because f of 4, let me instead of x put 4, because f of 4 is not equal limit f of x, where x approaches to 4. Therefore, it's not continuous, this function. Okay? This one was continuous. Let me type it here. Okay? All right. So, moving to this question, let's see. We are going to explore at the point of 3. What do we have? So, we have piecewise function here. 5 minus x at the point x is less 4, x is less than 3. Therefore, this light brown color, it's going to go only take parts of less than 3. And x plus 1, this blue color, dark blue color graph, and it's greater than x plus 3. Wherefrom I figured out that there is a hole. In both these conditions, we don't have equal sign. If I would have equal sign there in this condition, then there would be solid point, which means 3 would be included. So let's see on continuity and find one-sided limit. So I'm doing already one-sided limits based on graph. So limit f of x, where x approaches to 3 from the negative side. Let me the whole this limit put in the color so we will know what we are talking about. It's going to be equal how much? It's going to be equal 3, yes? Now, let's take care of blue one. Limit f of x, x approaches to 3 from the positive one, and it's going to be equal, oh, I'm sorry. This one is equal to, right? Look here, 2. And when approaching from the positive side, it's going to be equal 4. Obviously, the left side is not equal to the right side. So let me write down limit f of x, x approaches to 3 from negative side, does not equal limit f of x, x approaches to 3 from the positive side. Therefore, there is no, it's not continuous because there is an interruption. Let's say this piece, right? Interrupted, not continuous, and there is no limit at the point of 3. Does not exist. Okay? Next, question number 4. So, point I mark down with the dark green color. 6 minus x, that is less than 5. It's a blue color. And 1/5 of x, obviously it's gonna go under how to say, the slope is going to be much smaller, 1/5, and we are taking part x is greater than 5. So these conditions are limiting the usage of each function. Okay, so let's find out. So we have 0.5. It's approaching from the positive side. It's 1, right? Approaching from the left side. It's still 1. And limit at the point f of x is that it's undefined. Is undefined. Right? Looking from this, remember this very first example we were looking into, right here. It's undefined. All right, so what do we have here? It's undefined, when the function is not continuous. Why? Because f of 5 is equal how much? Let's assume it's 2. F of 5 this green point is equal to, right? And f of 5 does not equal limit x approaches to 5 f of x. Okay? Question number 5. So we have x squared. Here we have x squared parabola. Let me make it this color so we can see. Make it thicker, okay. And negative 4, it's going to be blue color. Say this is negative 4. So let's explore. So we have hole at the point of negative 2. It should be negative 2. This hole at x is equal negative 2. Okay? So when it's approaching to this hole from the left side, we get result how much? If this is negative 2, this will be 4, for example. We take 4. When it's approaching from the positive side to negative 2, it's going to still be 4, right? Okay, so at the limit from the f of x, x approaches to negative 2 does not exist because there is a hole. We can't step in, right? And it's not removable, this hole, because I don't have any how to simplify. So, and domain is from negative infinity to positive infinity for the x squared, right? Okay, because it's not removable, so it does not exist. And about continuity, at glance when you look, it looks continuous, but this negative 4 also, we have f of negative 2, it's equal negative 4, because f of negative 2 does not equal to limit f of x approaches to negative 2, therefore it's not continuous. Okay, I'm done. I hope this helped you and you understood. So thank you for watching, and I'll see you at next topic that I will record. Please, by your likes, show me that the topic is interesting to you and you like the way I explain. So this way it will help me to pick up the direction, which direction to go. All right.